Power series. Power series functions. Taylor and McLaurin, what questions do you have for me? Yes, ma'am.
11,
14 and 11.9. We're trying to find an expression for the ln of 1 minus x, right? So it says use equation 1. What's equation 1? Ah! That's equation 1. Now our goal is to find a power series for this. Yes? So how the hell are those two related? Almost. The derivative of ln of 1 minus x is I'm sorry, I can't quite hear you. So really, if I want to deal with this, I have that right here. Now you want to get this, you have to deal with the minus sign, you have to take the integral term by term, and then you're in exactly the right place. Okay. I am required to remind you of something very important. Properties of logarithms. I'm dividing inside an ln. What can I do? How? What's ln of 1? If you put 1/2 into your series, you can come up with an expression for ln of 2, can't you? Sneaky mother. There's a lot to be said for using a power series to calculate a logarithm. Like a fly with a sledgehammer is one of the things that comes to mind, but more questions.
Can we just do the setup for 11, 9, and 20?
Ew. That? I'm sorry?
Unless I'm just being dumb, it's easy.
You said 11 and 20. You said 11 and 20.
Yeah.
That's not the.
I'm perfectly happy to do it anyway, but I'm like, I've never seen this problem before. But my first reaction is to write this like this. Because this looks like it could come from here by taking a couple derivatives because there's a cube on the bottom. But that's okay. I start saying, how do I get a cube in the bottom? Well, 1 over 1 minus x. If I take the derivative of that, well, that's the same as 1 minus x to the negative 1, taking the derivative, minus 1 minus x to the negative 2. Wait, there's an extra minus sign. Those go away. No, the minus is what shows up. That's why the minus is there. No, the minus comes away. Minus comes from the negative 1. I'll be able to do this in my head, really. Then we do it again. So 1 over 1 minus x. Second derivative would be negative 2, 1 minus x to the negative 3, and then another negative. Aha. So this is a second derivative expression that relates back to this. Now I have a power series. I'll have to integrate twice instead of once, and then I'll have to multiply that part in. I've never seen this problem before. What are we doing? Wait a minute. Okay, now I can. Does that make sense, though? I want to relate it back to this one power series that I'm absolutely sure I know how to do when I see other powers of 1 minus x.
You just want to integrate it to the point where it was-
Yeah.
Okay.
I really don't want to try and do this by Taylor and Maclaurin unless they tell me to, and that prevents me from having to do that. If I can relate it back to my favorite geometric series, 1 over 1 minus x, then I'm going to run from there. So I would end up with this part, that's half of this, but this is the second derivative of 1 over 1 minus x. That's our power series.
Uh, 11 times 40.
40. The advantage to this problem is that I get to cheat. So I go back to the list of Maclaurin series on like 2 pages earlier. What's in there that kind of looks anything like x squared 1 plus log 1 plus x cubed? Okay, so we know ln of 1 plus x has a power series. What is it? Like that?
Yeah.
Okay. But this is ln of 1 plus x cubed. Replace this x by an x cubed. Then take that, put it into the series. Multiply it in.
Multiply that by everything.
Well, I mean, you're going to have an x to the something here, then you're going to get 2 more x's, aren't you? Yeah. Yeah, this is the best part of having this. Means I can do everything from that. Like we did with the e to the x becoming the e to the x squared. Yeah, I put in the x cubed where I see the x, and then I can adjust for this.
Go ahead and find the solution.
If you'll tell me what it is.
Find the Maclaurin series for f of x equals e to the 2x using the definition.
Okay, it says using the definition. That means I got to do the patterning thing. But I know what the answer should look like because I know what e to the 2x. F of x equals e to the 2x Maclaurin series. Okay, first thing, over here on the side of my page, I remind myself that e to the x is the sum x to the n over n factorial. That's the one off the table. So these are series you should know but don't have to. Well, if I just put in the 2x, just like I was just talking about with Dominic, hey, if I put a 2x up there, then e to the 2x would be the sum parentheses 2x to the n over n factorial, which is 2 to the n x to the n over n factorial. So that's where I should end up. But you said by the definition. By the definition means I need to take derivatives, I need to plug in 0, and I need to look for a pattern. The 0th derivative is the function itself. So the 0th derivative is e to the 2x. And when I put in 0, I get e to the 0, which is, yay. What is the first derivative of e to the 2x? There's no trap. So when I put in 0, I get 2. Keep going. All right, wait a minute. These are all powers of 2. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, and that matches exactly with the value of n. So I am going to make the following inductive argument. Looking at a bunch of examples, I'm going to draw forth a general rule. I believe the nth derivative should be 2 to the n e to the 2x. Therefore, the nth derivative at 0 will be 2 to the n. That means the next one should be 32, the one after that 64, and so on, right? Okay, now out comes Taylor's formula. My power series looks like the sum n from 0 to infinity, the nth derivative evaluated at our center over n factorial x minus the center to the n. Because we're doing a Maclaurin series, my center is 0. That formula should spill out of onto the paper as soon as you get it. That I guarantee you I'm going to need. So now I know what this is. That goes here. 2 to the n over n factorial, x to the n, lo and behold, it matches what I thought I would get.
The problem just asked like find the Maclaurin series and didn't say the definition you used.
Yep. But that requires you to memorize some of those things out of table 1, right? So there's a play there. And I am of the opinion that there is very little utility in memorizing power series until you do a lot of work with power series. And that usually comes in later courses than this. So I would be more likely to say you'll see this more than you'll see this, which really means that's the formula that has to be in there somewhere. Yeah. Actually, when Taylor writes it, he writes it with an A, but yes. Or if you'd rather remember just the coefficient, he writes Cn x minus a to the n, and Cn is the nth derivative at a over n factorial. 0 is for Maclaurin, A is for everything else. Taylor and Maclaurin are the most well-known series because they're the ones we introduce here, but there are several other types of series, different kinds of power series. There's several power series attributed to a gentleman by the name of Laurent. There's an entirely different set of series that instead of using powers of x, use trig functions. So you have cosine of nx and sine of nx instead of x to a power. And those are called Fourier series. French mathematician Brain started to say Joseph, and I don't think that's right. Fourier, who studied heat and heat distribution in differential equations. So there's some very interesting work in thermodynamics that are related to Fourier series. It turned out that a lot of what Fourier did became the basis for touch-tone recordings and sounds, and thus the telephone. Fourier series are used in audio reproduction, and they're what come out of most audio filtering. So when you play with GarageBand, you're actually doing a lot of power series work. Anyhow, sorry. More questions here. Should have brought my t-shirt. I'll bring it Monday. Cauchy actually worked at the connection between integrals and series, but again, another class. More questions. 11:09, 11:10, review sheet, hit me.
Can we do 3G in review? This summation, anything with 1. -1 to the n, sine of pi over n.
That's it? And all I want to know is if it converges or diverges, right? Okay. Clearly, I couldn't start at 0 because I'm dividing by n, and sine of divided by 0 is a bad idea. So, the hell just happened? Excuse me for a second. Let's see if I can figure out what happened to the camera. There it is. Okay, we're back. What kind of a series is this? Let me go through that big list. Is it a p-series? Is it a geometric series? Is it kind of like either of those? Well, I don't see 1 over n to a power or something 1 over something to a power. I don't see something to the nth except a -1, but I see a -1 to the n. That says alternating to me. So let's start there. If this is alternating, I'm going to try the alternating series test. Okay, what do I need for the alternating series test? Positive decreasing things, part of it, but I need more. There are two specific criteria for the alternating series test. Jacob? So what I need is I need Bn to be the absolute value of An, and then I need to know that the limit as n goes to infinity of Bn is 0, and I need to know that Bn plus 1 is smaller than Bn, so we are decreasing. Yes, I need to know decreasing. I need to know that the limit is 0. Those are my two pieces. So I take away the -1 to the n, I take the absolute value of sine of pi over n. Now, the reason I left the absolute value there is because sine goes between positive and negative, right? But I'm just not taking sine of anything. I'm taking sine of pi over n. So we're really looking at sine of pi over 2, sine of pi over 3, sine of pi over 4. Wait a minute. Those numbers get closer and closer to 0, don't they? Let me look at the limit. The limit, as n goes to infinity, sine of pi over n, even without the absolute value, is the limit, is the sine of the limit as n goes to infinity of pi over n. Why? Oh, way back in chapter 2, we said we could take limits inside continuous functions. What's this limit? Zero. Pi divided by something huge is 0, so this is sine of 0. What's sine of 0? Yay! That checks off the first one. And now I need to talk about decreasing. Wait a minute, what's sine of pi? That's 0. And sine of pi over 2 is 1. Sine of pi over 3, which is like 0.866 or something like that. Sine of pi over 4, 0.707. And then I start to get to ones I don't know. Right? I don't know what sine of pi over 5 is. So how do I know that this is decreasing? There are two different ways to know this is decreasing. One is to think about the graph of sine of x. We're going that way. As n gets bigger, we're going towards 0. Right? Where is sine of x? Sine of x is here. That's definitely decreasing, isn't it? The other way is to think of it on the unit circle. The sine is the y value. It's the height on the unit circle. Pi over 2, pi over 3, pi over 4, pi over 5, pi over 6. Yeah, we're going down the unit circle. Our sine is getting smaller as we get closer and closer to 0. We could also take the derivative of sine of pi over x. Ew. But that works because derivative sine is cosine pi over x, and then I get minus pi over x squared. For any positive value bigger than or equal to 2, this is positive. This is always negative. From some point on, my derivative is negative. So there are 3 different ways to show that this is decreasing. Hey, that means we get to go back up here, put a check mark. So by the alternating series test, my series converges. Ta-da! But like I said, the biggest problem in general with problems like problem 3 is which test do I use? What kind of series do I have? Remember the flowchart picture we found? Put on our Canvas page, use that flowchart. More questions. Eleven, 9, 12. Okay, it says first use partial fractions. So that's the very first thing we do. So let's do number 11. We'll do that the whole way through, all right? So 2x minus 4 over x squared minus 4x plus 3. So that's going to be a over x minus 3 plus b over x minus 1 to factor the denominator. So I have a x minus 1 plus b x minus 3 equals 2x minus 4. I now have to solve for a and b. Which method do you want me to do that with? What I could rearrange, or I can do the plugging in method. This side, I get -2, and on this side, I get 0 plus b times -2, therefore b is 1. If I plug in x equals 3, on this side I get +2, on this side I get a times 2 plus 0. And so that tells me that a is also 1. Wonderful. So I know 2x minus 4 over x squared minus 4x 3, 1 over x minus 3 plus 1 over x minus 1. So far, so good? Okay, here's the tough part. I need to turn both of those into geometric series. Oh, hang on a second. Remember, this is in the section about geometric series, so I'm going to start with my idea that 1 over 1 minus x is the sum x to the n. So that second fraction, the bottom's the wrong way around, isn't it? So let's reverse that by putting a minus on top. I'm going to do the same thing in the other fraction. That way the x is at the end in the denominator. It's subtracted, just like it's supposed to be for this formula. But in the bottom of that fraction, I have a 3, not a 1. What do I do to deal with that 3? Think back to what we did with polar conic sections. Needed a 1 and I didn't have it. What did I do? So I'm going to divide everything by 3. That means on top, this is negative 1/3, 1 minus x over 3. And this is negative 1 over 1 minus x. Ready? A over 1 minus r. That's a geometric series. Now here's the part that's a little finicky. I don't want 2 series. I want 1. So I need to gather my like terms. But that means that that first series should be written with just x to the n alone, so I can look at the coefficient and compare it to the coefficient in the second one. So I'm going to separate this fraction minus 1/3 times 1/3 to the n, x to the n. And then here, minus 1, x to the n. Ooh, both of these are negative, so I'm going to have a negative in front of this whole thing. These 3's can be combined. That'll give me a 3 to the n plus 1 in the bottom. If I pull the negative sign out here, then I'm adding 1, and I've gathered my like terms. And that goes from 0 to infinity. Talk to me about the algebra that you don't like. Ah, that makes a difference. At which point you make me doubt myself, so I go back and look. Well, this is not the one that is in the assignment. This is the one next to it. Yeah. Better, Norm? One of the things that we have a problem with is getting this to the point where it's combinable. And that's really why this is in this section, so I can say, hey, wait a minute, how do I do the algebra to make this one series? Well, oh, because it's 1 to whatever power. What's 1 to any power? So I could make it the 1/3 to the n plus 1, but I chose to put it just on the bottom because the top is always a 1. But you're absolutely right. You certainly could write that. That would be absolutely 100% correct. More questions? Yes, sir.
20s, I was looking at 28. I just noticed that that's not a sign.
In which section?
11.9. I was confused about like what to do with like just in general how to.
Okay, so the advantage to that problem is that we have a power series for the inverse tangent, right? And then I have a 1 over x, right?
Yeah.
So if I have a power series for the inverse tangent, all right, the power series for the inverse tangent is, somebody pull it out of the book table and read it to me. I think it's 1 over 2k plus 1, x to the 2k plus 1, and then there's a minus 1 to the k in there, but I'm not 100% sure.
It's -1 to the n times 2n plus 1 divided by 2n plus 1.
And that goes from 0 to infinity, right? Okay, then I'm going to divide by x. That means I have to divide the power series by x, yes? Well, what do I do to the x's that are in here? I have to get rid of one of them. So I subtract 1 from the power. You were asked to integrate this thing. I have no idea how to integrate this thing. But this is a power series. I know how to integrate a series. All of a sudden it gets a lot easier because I know what to do here. I can do the power rule when I do the integral. So it's a whole problem of setting up this into a way that I can go, oh, I know how to integrate this now. More questions. For those of you, yes, ma'am. For those of you moving on in calculus, it gets easier for you. Because this is unquestionably all the hard stuff. We're just going to need to use it later. Almost all of Calc 3 goes back to the ideas from Calc 1 again, just with more variables. Anyhow, yes. 16. So 16, like 20, is about manipulating the things we have to get something we can use, right? So we have a power series for the logarithm, yes? But it's a logarithm of 1 plus x, right? Oh, I'm looking at 5 instead of 16, 15. I'm looking at 15 to do something comparative. So I say to myself, hey, I have a power series for this. So the power series I have, though, ln of 1 plus x. Dominic, I'm going to ask you to give me this one again. So my question is, can I manipulate this to look like that? 5 minus x equals 1 plus something. Oh, we'll just make this 1 plus 4 minus x, right? Well, then I put that in here. So that's the power series I want to use. But then it asks me for the radius of convergence. Do the ratio test. Or look on the table. What's the radius of convergence for this? Okay, that means the radius of convergence for this should be 1. So that means that 4 minus x less than 1. If I multiply through by a minus, I flip the direction. There's my interval of convergence. I would have to check the n specifically, but since it just asked for the radius, it should be 1. I can do the ratio test to check.
How would we do that if we didn't have these memorized?
I'd be in deep shape. What I would have to do is I'd have to generate the Maclaurin series or the Taylor series, or I'd have to do something that related this. This is an 11.9, isn't it?
Yeah.
Oh, wait a second. I shouldn't have done it with the Taylor series. I apologize. Let's try this again. All right. ln of 5 minus x. Since this is just in the section on general power series, let's take the derivative. What's f prime? Leo?
It would be 1 over 5 minus x times negative 1.
Okay. I'll play the same game we were playing in the partial fractions. This is negative 1/5 over 1 minus x over 5. So far, so good. A over 1 minus r, turn that into geometric. Which I will then do the same thing we did before. Minus 1 over 5 to 1 extra n, x to the n. But that's f prime, so f is the integral of this. There we go, Dominic. Now I didn't need to do anything about having anything memorized except my geometric idea. Integral gets moved inside. So I take the antiderivative of x to the n. Negative 1 over 5 to the n plus 1 times 1 over n plus 1, x to the n plus 1. And then there should be a plus c somewhere. I should figure out the value of C. Easiest way to do that is to plug in something that's going to cause all of these to cancel out. And in this case, that would be 0, right? If x equals 0, then that whole right-hand side becomes the sum of a bunch of zeros and a C. But what if we plug in 0 at the top? What do I get there? The ln of 5. So my power series is ln 5 plus the sum from 0 to infinity, negative 1 over 5 to the n plus 1, 1 over n plus 1, x to the n plus 1. There's my plus C. I found it. Thank you for pointing that out, Dominic. I did it the wrong way. Which goes back to my statement back in chapter 7, there's usually more than one way to skin a cat. Now, in the problem we are looking at with the tangent inverse of x cubed, well, the derivative of tangent inverse of x is 1 over 1 plus x squared. I remember that. We actually did that one in class on Wednesday. So I know how to get the tangent inverses of power series using this same integral idea. What do I do with the extra x cubed? X squared? X squared. What do I do with the extra x squared? Try a U sub, you'll see some really nice things happen. More questions? I will give you all the extra 2 minutes. I will see you all on Monday. I hope you have a wonderful weekend. If you've got questions, see me in office hours this afternoon or send me emails. We'll see you Monday.